Hello, my name is Jessica Medro, and my project is focused on the role of NOD-like receptor X1, or NLRX1, in environmental pollutant-induced lung inflammation. Environmental pollutants are a heterogeneous mixture of gaseous and particulate matter. While the impacts of individual components of environmental pollution have received substantial attention, the impact of inhalation co-exposures is poorly understood. Ozone is one of the most toxic and reactive gaseous components of air pollution. Acute ozone exposure has been found to aggravate chronic lung diseases such as cystic fibrosis and asthma in susceptible populations. Ultrafine carbon black is a significant environmental and occupational hazard. The interaction of ozone and carbon black can synergistically induce more toxicities and lung function decline. NLRX1 is a recently discovered protein belonging to the NOD-like receptor family and has been reported to negatively impact inflammatory responses. My focus is on understanding the mechanistic role of NLRX1 in carbon black and ozone-induced lung toxicity. Therefore, we hypothesize that NLRX1 can significantly inhibit carbon black and ozone-induced lung inflammation and lung function. For this project, we use C57 black 6 mice as wild-type and NLRX1 knockout mice. The animals were randomly divided and exposed to filtered air as the control, or 2.5 megs per meter cubed and 1 ppm ozone for 3 hours, followed by euthanization 24 hours post-exposure. Figure 4 demonstrates lung function measurements using Flexident system. The data indicates a significant increase in lung resistance, or RRS, as in the figure, and decline in forced expiratory volume, or FEV 0.1 after methylcholine provocation in NLRX1 knockout mice compared to wild-type mice after co-exposure. Figure 6 contains the bronchoalveolar lavage fluid data. In figures A and B, you can see the total cell and macrophage counts are significantly higher in NLRX1 knockout mice as compared to the control. And interestingly, the data indicated a significant increase in neutrophils in mice lacking NLRX1 as compared to the wild-type mice post-co-exposure. This indicates that there is a significant inflammation in NLRX1 knockout mice as compared to the wild-type animals. Now, figure 5 shows the macrophage and neutrophil population in the bronchoalveolar lavage fluid. Next, we performed real-time PCR in the lung tissues to identify the fold changes in inflammatory genes. Figures A and B represent a significantly high gene expression at the mRNA level of the inflammatory genes TNF-alpha and IL-6. Figure 8 represents the gels that I ran to identify the wild-type mice and the NLRX1 knockout mice, which we breed at WVU. Therefore, in conclusion, we have established that co-exposure causes significant increase in neutrophilic infiltration and decline in lung function in NLRX1 knockout mice compared to the wild-type mice. We also found that NLRX1 knockout mice demonstrate significantly higher expression of inflammatory genes compared to wild-type mice followed by co-exposure. In future, we plan to quantify the inflammatory proteins after co-exposure in NLRX1 knockout mice via techniques like Western blot and ELISA. Further, we would also like to perform macrophage polarization studies in NLRX1 knockout and wild-type mice followed by co-exposure. Additionally, we plan to assess the mechanistic role of NLRX1 in mitochondrial damage induced by co-exposure. I would like to thank Dr. Hussain for his guidance, the WVU Inhalation Facility, Travis Goldsmith, and Kevin Engels for their excellent technical assistance.